Hello everyone, in this Thierry Sicard tutorial number 55, we will review the voltage, gain and phase versus frequency for three different common mode amplifiers, and we will do a special focus on the case with the bad zero. We will examine the common source amplifier using a NMOS in three different cases. The first with a capacitor C between the gate and drain, the second with a capacitor C between the drain and ground and a resistor R in series, the third with a single capacitor C between the drain and ground. We can realize the small signal diagram with a transconductance Gm. The capacitor current IC is equal to Gm Vi plus Vout over R. The capacitor voltage Vc is equal to IC times 1 over Jc omega. Since Vc equal Vi minus Vout, we can write the following equation. The Gm over Jc omega term is multiplied and divided by R to obtain the DC gain GMR. After rearranging the equation, we obtain the gain Vout over Vin. The final gain equation is in the yellow box where the DC gain term is factored out. Let us now calculate the gain of the second case with capacitor C between drain and ground and a resistor R in series. As in the first case, we establish the small signal circuit with a transconductance Gm. We first calculate the output impedance Z0, then the output voltage V0. Substituting Z0, we obtain the equation Vout as a function of Vin. After some adjustment, we obtain the gain equation in the yellow box. Finally, we perform the gain calculation of the third case with a simple capacitor C between the drain and ground. We do the same with the calculation of the output impedance Zout, then Vout, to obtain the final gain equation in the yellow frame. It's time to compare these three gains by plotting the low frequency curve. In the first case, we notice that the pole omega p is equal to 1 over Rc, denoted in red, and Rc is underlined in red in the gain equation. In the second case, since R is small compared to the capital letter R, the pole omega p is equal to 1 over Rc, denoted in red, and Rc is underlined in red in the gain equation. We do the same for the third case and see that these three schematics have the same omega p pole equal to 1 over Rc. If we continue the plot at high frequency for the first two cases, we will see no difference with a minimum gain of 0 dB for both cases. Differences will begin to appear between cases 1 and 2 if we plot the phase of Vout as a function of Vin. In the first case, the phase continues to reach 0 degrees at the angular frequency omega 0 equal to Gm over C. For the same angular frequency omega 0, the phase in the second case returns to 180 degrees. The third case is different because since capacitor C is ideal without any series parasitic resistance, the gain continues to drop below 0 dB, so the phase remains at 90 degrees and has no zero. In the first case, this zero is called a bad zero because the phase continues to shift up to 180 degrees with the gain limited to unity. This bad zero is due to the negative sign in the equation represented by the red circle. In this slide, we will analyze with more details the bad zero case number 1 with the voltage gain and both schematics shown on the right side. The Vout over Vin gain equation can be transformed in 3 different equations based on low, medium, or high frequencies. Let's start with the low frequency. In the gain equation, since the Jc omega over Gm term highlighted in yellow is very small compared to 1, the low frequency gain equation can be simply be minus GMR over 1 plus JRC omega. So the gain equation only has the pole omega p equal 1 over RC. At this angular frequency omega p equal 1 over RC, the gain is minus 3 dB relative to the asymptote and the phase is 135 or 180 minus 45 degrees. It can be noted that at the angular frequency omega p divided by 2, the gain is minus 1 dB relative to the horizontal asymptote, which means the DC gain, and the phase is 153 degrees, which means 180 minus 27 degrees. When the angular frequency omega p equal 1 over RC is multiplied by 2, the gain is minus 1 dB relative to the asymptote of minus 20 dB per decade, or a gain of minus 7 dB relative to the DC gain, and the phase is 117 degrees or 180 minus 63 degrees. The yellow color highlights this first part described by the gain equation minus GMR over 1 plus JRC omega. At the middle frequency, that is between the angular frequency interval omega p and omega 0, JRC omega is much greater than 1, thus 1 plus JRC omega is equal to JRC omega. We can remove the term 1 from the denominator. The gain equation can therefore be written as the first term plus 1. Since this term is much greater than 1, the gain at the middle frequency is minus Gm over Jc omega, represented by an asymptote of minus 20 dB per decade. The orange color highlights the middle frequency portion described by the gain equation minus Gm over Jc omega. The voltage gain equation Vout over Vin is shown in the yellow box. It can also be written as follows. JRC omega being much greater than 1, the term 1 plus JRC omega can be replaced by JRC omega. Thus, at high frequencies, the gain is written 1 minus Gm over Jc omega, where the angular frequency omega 0 is Gm over C with a phase of 45 degrees. When the angular frequency omega 0 is multiplied by 2, the gain is plus 1 dB over the horizontal asymptote of 0 dB and the phase is 27 degrees. When the angular frequency omega 0 is divided by 2, the gain is plus 1 dB at the asymptote of minus 20 dB per decade or plus 7 dB and the phase is 63 degrees. The red color highlights the high frequency portion described by the gain equation 1 minus Gm over Jc omega. I want to thank you for your attention. On my next Thierry Sicard tutorial number 56, we will be more focused on the bad zero explanations. So see you soon and stay tuned.